Welcome back to day 2 of Geometry 7-2, Similarity and Transformations. Today we're going to use the properties of similarity transformations to determine whether polygons are similar. And we're going to use the properties of similarity transformations to prove circles are similar. Okay, let's determine whether polygons are similar. We might receive the information strictly in a set of ordered pairs, like you see here in example A. In your notes, I actually have left you with the images that were drawn for you. So if you don't have the images drawn for you, what could you do? You could draw the images, right? So here is what you see when we plot the points for the quadrilateral ABCD and the quadrilateral HJKL. Okay? So that's what you see, and when you have it on a coordinate plane, it's pretty easy to check out the ratios to see if the polygons are similar, right? We can compare the corresponding sides. We could also, though, if we didn't have that diagram of the images, we could just look at the values in the ordered pairs for corresponding vertices. So A should correspond with H, right? Could we find a factor that could take us from -6 to -2? And yeah, the factor would be 1/3, right? How about from -6 to -2, the second coordinate? And there it is. It would be 1/3 again. Let's see if that same factor works for the second vertices B and J. -6 times 1/3 is -2, right? And 3 times 1/3, is that 1? Yes, it is. So we could continue checking out all of the vertices. 3 times 1/3 is 1. 3 times 1/3 is 1. And finally, 3 times 1/3 is 1. And -6 times 1/3 is -2. So we can see algebraically that ABCD maps to HJKL by the dilation of a factor of 1/3 for each of the coordinates, right? Oops. So another way to do it, as I said, would be to, with the diagram, compare the corresponding sides. So we have a length of, right here, we have a length of 9 to 3. Is that equal to the length of 9 to 3? And yes, it is, right? That proportion is the same. Let's see. Here we have the coordinates for a second example. And in the diagram, if you were to plot these, you would see what looks like two rectangles, right? And so we could look for the ratios here to see if we have proportional ratios. Let's look at what appears to be QR and XY. So we have a length of 2 to 3, right? 2 to 3. Is that equal to this length here, which is 4 to 10? And that isn't, is it? So the ratio of these corresponding sides does not equal the ratio of those corresponding sides. So we might be able to, come up with a ratio for two sides, but it isn't going to work for all sides. So this is not a pair of similar quadrilaterals. Next, example C, we have triangles. And so if we were to plot the two triangles given, we see ABC and down here DEF. So this is interesting because when we look at the math, 1 times what gives you 4? Well, 1 times 4, right? But 2 times 4 doesn't give you 6. But don't they look rather similar? Let's check it out using our corresponding sides. Side length AC is 2, and the corresponding side DF is 4. 2 to 4. Let's check out this bottom, right? We have 1 to 2. Well, 2 to 4 equals 1 to 2, right? Interesting. And so it looks like we have more than one transformation taking place. There's a dilation, right? Looks like a factor of 2. And yet when we multiply by 2, we don't get here. So there had to be a second transformation. And what happened was we have a translation. Okay, so the triangle has slid down and then maps by the factor of 2 to the new triangle D, E, F. So, very cool. We saw the factor was 2, but we needed to move the triangle, translate it, in order to then apply the dilation factor of 2. Okay, and in this case we have a quadrilateral FGHJ mapping to a quadrilateral STUV. Okay, so once again it looks like there's been possibly 2 transformations. We could check out the proportion. Let's check out G to F. We have 3 to what appears to be TS, which is 1. 3 to 1. Let's see, if we go from H to J, we have, what, 6? And on this side we have 2. So 3 to 1 does equal 6 to 2. So it looks to be proportional, and yet we have what appears to be points that are across the y-axis. So what do we call that? Yes, we call that a reflection in the y-axis, right? So this figure has been reflected, and then there's a dilation from the reflected to our new image. And so FJHJ maps by reflection in the y-axis, which means the opposite x value, right? And then dilated by a factor less than 1, you see it's a shrink, huh, of 1/3. So let's prove that circle A is similar to circle B. Well, we know that if we're similar, we have this same shape, but not necessarily the same size. And if by definition we have a circle, then we have the same shape, don't we? So how can we show that circle A with center 0, 0 and a radius of 1 is similar to circle B? Well, the center, if we're going from circle A to B, the center has slid up, hasn't it? And it's slid up 6 units. So we have a translation 6 units up. And then once, if we were to move that circle up there, again, it has a radius of 1. And the new circle has what type of a radius? Let's see. So that's going to factor into our dilation, isn't it? So the circle A can be mapped by a translation up 6, and then circle A can be mapped to circle B by dilation of a scale factor of 3, right? So they are similar. Okay. Here's a second question. If we have a circle C with a center at 0, -3 and a radius of 2, let's show that it's similar to circle D with a center at 5, 1 and a radius of 5. So these blue circles show our figures, and we know that if we start at C and we're trying to get to circle D, we're going to have to translate the circle, and that's where we see C prime here. So how do we translate C to this location where the center is point D? We're going to have to go up and to the right. Okay, so we will show that by moving to the right 5 and moving up 4. So there's our first translation. And then we're going to move from a radius of 2 to the radius of 5, right? And what will that factor be? That's right, a factor of 2.5. So circle C and circle D are similar. Here's a simple little application for similar figures. Eric wants to make a drawing to show how he will arrange 3 rugs in his room. The large rug is twice the size of each small rug. Eric will first draw the small rug in the lower left corner and the large rug in the middle. So how can he draw those? Well, easiest thing would be to allow the room to be on a coordinate plane, right? And we would place maybe this lower left corner at the coordinate 0, 0, right? And then we could just take a small rug and place it in that corner. Draw yourself the rug. And then we could apply the dilation. Since the scale factor is 2, we could multiply each of the vertices of the small rug by a factor of 2, right? And then we can place the large rug in that location. Go ahead and pause the video and come back and check your answers. Nope, doesn't work for each vertex, right? And number 2, yes, we have a reflection and then a dilation by a factor of 1.5. And again, pause, come back and check. And I hope maybe you drew this and you could see that we have a translation and then we have a scale factor of 1.5 or 3/2. So they are similar. And there you go. Have a good day.